Jeff Disher here again. Today I'm going to talk about sorting as a lead into a specific talk I'm going to do on merge sort next. So first of all, the basics behind sorting. Well, why would you do this? But it turns out that this is actually a very common problem in computer science for reasons which are obvious, like sorting for output. You want to get the list of all the employees alphabetically. That's a sort. That thing's very common and people are very used to how that works and seeing things like that. But there's other reasons as well why you might do sorting as part of another operation. For example, if you have two lists of data and you want to find out how many elements they have in common, well, if they're not sorted, you're going to have to compare each one of those elements to each of the ones in the other list. This could be very expensive. If you sort the data first, it actually makes it very, very fast to do that operation, because you only have to compare against the next one, not all of them. The concerns that come up with different sorting algorithms are based around efficiency. There's the time efficiency, how long is it going to take, how many operations are done, the space, does it require that you allocate lots of extra memory to get it done properly or quickly, the locality, which is an issue which matters for CPU caches. Is the memory that you're touching all really close together at roughly the same point in time to get real benefit of the CPU cache? And also versatility. Is there anything about the environment you're working with that can get some benefit from a certain detail of an algorithm, or is there some detail of an algorithm which makes it completely inappropriate for your environment? And because of all these concerns, there's no one solution to this, which is actually kind of interesting. There's still a lot of work going on in this area today. So first of all, complexity. Now, complexity is the measurement of the cost of something as it grows, as input size grow infinitely, essentially. So we use big O notation. So the cost is a function of n input size. So for n elements in a list, you're going to have a certain cost that's expressed as what's called a big O. So for example, simple sort algorithms usually come down to the big O of n squared, meaning that roughly you're comparing each item with each other item. This is very expensive because it means that for every one element you add to the input list, you're now doing another n comparisons. The more advanced ones that are done within most actual situations where data gets very large are n log n, where the log is usually a base 2 logarithm. So it's usually based on a partitioning of the data, cutting it in half in some way, such that it can avoid extraneous comparisons by making strong statements about subcomponents of the data. These are quite clever, and it's something that a lot of people really get into. So beyond that, there's actually a class of algorithms which is kind of unfortunately ignored, which is the specialized algorithms, which have a quasi-linear time cost. So the big O of mn, where m is some constant. And this is based on performing an iterative arrangement instead of comparison. Now, unfortunately, these algorithms also don't apply in many situations. This is part of why they're overlooked a lot. But things like radix sort are very interesting in that area. So to think about sorting from a human point of view, how does it start out? What's the simplest way of looking at this problem? Well, typically, humans use what's actually called an insertion sort. This is actually used in computers from time to time for small data sets as well, because it's very, very simple, and there's very low cost overhead for small pieces of data. Now, this is something where you create a sorted list one element at a time. So it's like someone's handing you a bunch of cards. You get your cards, you sort them, so you start picking one and moving it to the other side, which is now your sorted list, and now you're building the sorted list one at a time, taking one card and finding the right place in the sorted list to put it. This is really common. Plus, it's something you can do in what's called online, which means you can sort as you get the data, which, when you're sitting at a table playing a game of cards, is usually what's happening. The dealer's handing you one card at a time. Well, you can sort it online. You can sort it as the data comes in, meaning that as soon as they've finished dealing, you've already sorted. You don't have to start, which is how a lot of other algorithms would work. So this is really great for sorting things like a hand of cards. Now, it doesn't really scale, though. If you were going to sort 1,000,000 cards this way, it would be really slow, because you'd keep, for each one of the 1,000,000 cards, by the time you get to the end and you're taking the last card, now you had 1,000,000 elements in this sorted list, and you had to go find where to put this one. That finding operation is really time-consuming. So it doesn't work for large things, but it works really well for small things. Even in actual practice in computers, they use it all the time. So in a computer, how do you look at this? What's the benefit we get there? Well, usually you try and limit the comparisons. This is where we get the n log n runtime. It's usually based on finding ways that you can ignore things around it. So quicksort is a common one. It works in n log n runtime. It's based on the idea that you can recursively partition data into the low half and the high half. So you pick some number, called a pivot, go over your list, and anything that's lower, you move it to the low part, anything higher, move it to the high part. Then you sort each of those sublists independently. And this means that, okay, yeah, you do a bunch of passes over the data, but only as many times as you can cut the data in half. That's why it's n log n. That's also why it's fast. So it's quite clever. Merge sort's another one, which is historically was used for a lot of things, and is actually making a bit of a comeback in a lot of modern algorithms and implementations. So this is based on the idea that you can recursively merge sorted sublists. So it's the idea that, okay, you take two elements, you sort them. Or you start with one element sorted. Add another element, you sort them. Now you get two lists of two. It's easy to sort those together as you merge them because you only have to look at each element once. So this is really something that it has an n log n runtime as well, but it also has certain other benefits, and I'll get into that in a later talk. So the hybrid approach is also realistically how people actually do this. So things like quicksort and merge sort, they have what's called a high constant overhead factor, which means that when the data gets really large, the constant factor doesn't matter. It's all about the n log n, and that's really, really good, so it's great. But when it's really small, the n log n might be smaller than the constant. So that's why usually what you use these days is, in fact, I was reading recently that in next version of Java, they're going to be using, their array sort algorithm will actually be a merge sort, which when it gets to a sufficiently small set of data in the merge, it'll actually use an insertion sort, just like a human does, because it's really fast for really small pieces of data. So this is really common. So some other concerns that come up. There's something called stability. Does resorting destroy previous sorted data? If you have a list of people's names along with their favorite colors, you sort by name, and then you sort by favorite color, does that destroy the sorting you already had, or are they still alphabetized within each color? It's important for certain pieces of data. There's also parallelism, because these days we have lots and lots of CPUs, but the CPUs aren't getting much faster individually. So can we split up the data, put it out on different CPUs, have them work independently? This is part of why things like merge sort are making a real comeback, but other algorithms like quicksort can be used in this way as well. And then there's locality. How well is cache leveraged? Most sorting algorithms are actually pretty good with this. Merge sort's specifically really good. Quicksort's pretty good as well. And it's important because the distance between cache and memory, CPU and memory, is getting bigger all the time. So using the cache effectively makes things faster. And also, there's something which is often overlooked, but the best case behavior. What if the data you're getting is already mostly sorted anyway? Well, it would be really wasteful to spend a lot of time running this huge sorting algorithm that changes nothing. So some algorithms have this interesting property where, well, if the data is already sorted or mostly sorted, it's really, really fast. So things like insertion sort and merge sort actually has that property as well. Things like quicksort don't work well in that environment. So this is another thing that's fairly important, and because data is it's quite frequently mostly sorted for various reasons, like you already operated on it, this is an important factor. So I hope that's a basic sort of primer on sorting and why it's important and why people talk a lot about it. And if you ever get into computer science, it's things that people spend a great deal of time talking about. It's a great area of discussion. There's a lot of new design and new ideas that are coming out there all the time, and new ways of rethinking old ideas such that they can be reborn again in a new era where they're suddenly important again. So I'll get into merge sort specifically in my next talk, but send me an email if you have any requests or post comments to the thread. Talk to you later. Bye.